Hello and welcome to Math Zone African Motives. In this tutorial, we'll be tackling question 7 on heat from an engineering science N4 question paper. We will cover topics including the volumetric coefficient of expansion, thermal area expansion, expansion of liquids, Boyle's law, and Gay-Lussac's law. Let's begin with the first part of the question. Question 7.1 asks us to define the volumetric coefficient of expansion, Ju. This question is worth 2 marks. To start, we'll consult the marking guideline for the precise definition. The guideline defines it as the increase of a unit volume of the substance per degree change in temperature. Let's break that down. The volumetric coefficient of expansion, represented by the Greek letter gamma, is a measure of how much a substance's volume changes for each degree its temperature changes. In other words, it quantifies how well a material expands in 3 dimensions when it's heated, or contracts when it's cooled. The formula that includes gamma is the volumetric expansion formula. It states that the change in volume, delta 5, is equal to the volumetric coefficient gamma, multiplied by the original volume V0, and the change in temperature delta T. This formula directly reflects the definition we've discussed. So our final answer for question 7.1, following the marking guideline, is that the volumetric coefficient of expansion is the increase of a unit volume of the substance per degree change in temperature. Moving on to question 7.2. The question reads, a rectangular steel plate has dimensions 500 mm by 700 mm at a temperature of 29 degrees Celsius. Calculate the area of the plate at a temperature of 159 degrees Celsius. Take the coefficient of linear expansion as 13 times 10 to the power of -6 per degree Celsius. This is a problem of thermal area expansion. The first step is always to identify the given information and the unknown we need to find. We are given the initial temperature, T0, as 29 degrees Celsius, and the final temperature, Tf, as 159 degrees Celsius. We have the dimensions of the plate. L0 equals 500 millimeters and W0 equals 700 millimeters, both at the initial temperature. Finally, we're given the coefficient of linear expansion, alpha, as 13 times 10 to the power of -6 per degree Celsius. Our goal is to find the final area, AF. Next, we'll consult our formula sheet for the relevant equations. For area expansion, we need the coefficient of area expansion, V, and the area expansion formula. The formula sheet provides 2 key relationships. First, the coefficient of area expansion, V, is twice the coefficient of linear expansion. Second, the final area AF is equal to the product of the initial area A0 and the quantity 1 plus V times the change in temperature delta T. The marking guideline also shows an equivalent formula. AF equals A0 times V times delta T plus A0. Both are correct. With our data and formulas, we can now solve the problem step by step. First, let's find the initial area, A0. The plate is rectangular, so its area is length times width. A0 equals L0 times W0. This is 500 millimeters times 700 millimeters. Calculating this gives us an initial area of 350,000 square millimeters. It's good practice to convert this to square meters right away to avoid large numbers and work in SI units, as is implied by the coefficient of linear expansion's unit of inverse degrees Celsius. Since there are 1,000 millimeters in 1 meter, there are 1,000 squared, or 1 million, square millimeters in 1 square meter. So 350,000 square millimeters divided by 1 million gives us an initial area of 0.35 square meters. The marking guideline confirms this step. Next, let's calculate the change in temperature, delta T. This is the final temperature minus the initial temperature. Delta T equals TOC or minus T0, which is 159 degrees Celsius minus 29 degrees Celsius. This gives us a change in temperature of 130 degrees Celsius. Now we have the initial area and the change in temperature. Let's find the final area. We will use the marking guideline's preferred formula for final area. But first, we need to calculate the coefficient of area expansion, beta. From our formula sheet, beta is equal to 2 times alpha. Plugging in the given value for alpha, we get beta equals 2 times 13 times 10 to the -6 per degree Celsius. This gives us a coefficient of area expansion of 26 times 10 to the -6 per degree Celsius. The marking guideline confirms this result. Now we can plug all our values into the formula. AF equals A naught times beta times delta T plus A naught. This formula represents the initial area plus the increase in area due to expansion. Substituting the values. A naught is 0.35 square meters. Beta is 26 times 10 to the negative 6 per degree Celsius. Delta T is 130 degrees Celsius, and A naught is 0.35 square meters again. Notice the degrees Celsius unit cancels out. Calculating the product A naught beta delta T first, we get 0.9011183. Then we add the initial area of 0.35. The final area is 0.351183 square meters. The question doesn't specify rounding, but standard practice in engineering is to round to a reasonable number of decimal places or significant figures. The marking guideline rounds to 3 decimal places. Let's do the same. So, the final answer is 0.351 square meters. This means the plate's area increased by approximately 0.001 square meters. We have successfully calculated the final area of the plate. This concludes question 7.2. Let's move to question 7.3. The question states, a container with a capacity of 1 liter of water is heated from 12 degrees Celsius to 47 degrees Celsius. If the container is completely full at 12 degrees Celsius and the volumetric capacity coefficient of water at 47 degrees Celsius is 385 times 10 to the negative 6 per degree Celsius, calculate the volumetric expansion. This problem deals with the thermal expansion of a liquid. It has 2 parts, calculating the volumetric expansion of the water and determining the overflow. First, let's list our given values. We have the initial volume of the water, V naught, which is the container's capacity, 1 liter. The initial temperature is 12 degrees Celsius, and the final temperature is 47 degrees Celsius. The volumetric expansion coefficient for water, gamma du, is 385 times 10 to the negative 6 per degree Celsius. We need to find the change in volume, delta 5, for part 7.3.1, and the overflow for part 7.3.2. Before we proceed, we must convert the initial volume from liters to the standard SI unit, cubic meters. Or, for this particular problem, cubic centimeters is more convenient since the volumetric coefficient is in per degree Celsius. We know that 1 liter is equal to 1,000 cubic centimeters. So our initial volume V naught is 1,000 cubic centimeters. Now let's find the relevant formulas on our sheet for liquid expansion. The only formula we need for this part is for volumetric expansion. Delta 5 equals gamma times V naught times delta TE. We will use this to calculate how much the water's volume increases. With our data converted and formula ready, we can solve the first part. Let's first calculate the change in temperature, delta T. This is the final temperature minus the initial temperature. Delta T is 47 degrees Celsius minus 12 degrees Celsius, which gives us 35 degrees Celsius. Now we use the formula for the volumetric expansion of the water. We substitute the values. Gamma W is 385 times 10 to the negative 6 per degree Celsius. V naught is 1,000 cubic centimeters, and delta T is 35 degrees Celsius. Notice again how the degrees Celsius unit cancels out. Multiplying these 3 numbers together gives us the volumetric expansion of the water, which is 13.475 cubic centimeters. This matches the marking guideline perfectly. So the volume of the water is increased by 13.475 cubic centimeters. Now for the second part, 7.3.2, which asks for the overflow. The problem states the container is completely full at 12 degrees Celsius. When we heat it to 47 degrees Celsius, the water expands. The container also expands, but typically the expansion of liquids is significantly greater than that of solids. Therefore, the water will expand more than the container. The amount of water that overflows is the total expansion of the water minus the expansion of the container. However, in Engineering Science N4, we often assume the container's expansion is negligible unless explicitly stated otherwise. So we will make the common assumption that the overflow is equal to the volumetric expansion of the water. Therefore, the overflow is simply 13.475 cubic centimeters. The marking guideline confirms this assumption and result, which is worth 1 mark. So the overflow is 13.475 cubic centimeters. This completes question 7.3. Let's move on to question 7.4. The question reads, a quantity of gas occupying 0.35 cubic meters at a pressure of 103.5 kilopascals is compressed isothermally to a pressure of 1650 kilopascals. Calculate the final volume of the gas. This is a problem involving Boyle's law. The key term here is isothermally, which means the temperature of the gas remains constant during the compression. Let's list our given information. We have an initial volume, V1, of 0.35 cubic meters and an initial pressure, P1, of 103.5 kilopascals. The final pressure, P2, is 1650 kilopascals. We are asked to find the final volume, V2. Now let's find the relevant formula on our formula sheet. We are looking for an equation that relates pressure and volume when temperature is constant. We find the combined gas law formula, which is P1V1 over T1 equals P2V2 over T2. For an isothermal process, the initial temperature T1 is equal to the final temperature T2. Because of this, we can cancel them out from both sides of the equation. This simplified equation, P1V1 equals P2V2, is Boyle's law. It states that for a fixed amount of gas at constant temperature, the pressure and volume are inversely proportional. Now we have our formula and all the necessary data. Let's solve for V2. We'll use Boyle's law to calculate the final volume. Our equation is P1V1 equals P2V2. We need to solve for V2. To isolate V2, we divide both sides of the equation by P2. This gives us V2 equals the product P1V1 divided by P2. Now we can substitute our given values into this formula. V2 equals 103.5 kilopascals times 0.35 cubic meters, all divided by 1650 kilopascals. Notice that because we are dividing, the units of kilopascals cancel out, leaving us with cubic meters, which is the correct unit for volume. Performing the calculation, 103.5 times 0.35 is 36.22. Dividing that by 1650 gives us approximately 0.02195 cubic meters. The marking guideline rounds this to 3 decimal places. So the final volume, V2, is 0.022 cubic meters. Therefore, the final volume of the gas is 0.022 cubic meters. This result makes sense. As we increased the pressure significantly, the volume decreased, as predicted by Boyle's law. This concludes question 7.4. We've reached the final question, 7.5. It reads, a cylinder contains 0.208 cubic meters of air at 1950 kilopascals at a temperature of 20 degrees Celsius. The temperature decreases to 2 degrees Celsius while the volume remains constant. Determine the pressure at 2 degrees Celsius. This is a problem involving Gay-Lussac's law. The key term here is while the volume remains constant. Let's identify our given information. We have an initial pressure, P1, of 1950 kilopascals and an initial temperature, T1, of 20 degrees Celsius. The volume is constant. The final temperature, T2, is 2 degrees Celsius. We need to find the final pressure, P2. A very important rule for all gas laws that include temperature is that the temperature must be in the absolute Kelvin scale, not Celsius. This is a common point where mistakes are made. The conversion from Celsius to Kelvin is simple. Kelvin equals Celsius plus 273. So T1 is 20 plus 73, which is 293 Kelvin. And T2 is 2 plus 73, which is 75 Kelvin. The marking guideline correctly shows this crucial conversion. Now, let's find the relevant formula on our formula sheet. We need an equation relating pressure and temperature when volume is constant. We use the same combined gas law formula as before. Since the volume is constant, V1 equals V2. We can cancel them out from both sides, leaving us with P1 over T1 equals P2 over T2. This simplified equation is Gay-Lussac's law, which states that for a fixed amount of gas at constant volume, the pressure is directly proportional to the absolute temperature. This means that if you decrease the temperature, the pressure will also decrease. We have our formula and all our data, including the correct Kelvin temperatures. Let's solve for P2. We'll use Gay-Lussac's law to find the final pressure. Our equation is P1 over T1 equals P2 over T2. We need to solve for P2. To isolate P2, we can multiply both sides of the equation by T2. This gives us P2 equals P1 times T2 divided by T1. Now we substitute our values into this formula. It's crucial to use the temperatures in Kelvin. P2 equals 1950 kilopascals times 275 Kelvin, all divided by 293 Kelvin. The units of Kelvin cancel out, leaving us with kilopascals, which is the correct unit for pressure. Performing the calculation, the numerator is 1950 times 275, which is 536,250. Dividing that by 293 gives us approximately 1830.20478 kilopascals. The marking guideline rounds this to 3 decimal places. So, the final pressure, P2, is 1830.205 kilopascals. Therefore, the pressure at 2 degrees Celsius is 1830.205 kilopascals. We can see the pressure decreased, which aligns with Gay-Lussac's law, as the temperature decreased. This completes question 7.5. Let's quickly recap what we've accomplished in this session. We started by defining the volumetric coefficient of expansion. Then we solved a problem involving thermal area expansion of a steel plate. After that, we calculated the expansion of water and the resulting overflow when heated. Finally, we applied the ideal gas laws, specifically Boyle's law for isothermal compression and Gay-Lussac's law for a constant volume process, to find an unknown volume and pressure respectively. We saw the importance of converting temperature to Kelvin for gas law problems. We followed the provided question paper and marking guideline meticulously, ensuring every step was explained clearly. We even corrected a minor oversight in the marking guideline's assumption about container expansion for part 7.3. Thank you for watching. I hope this detailed walkthrough has been helpful for your studies in Engineering Science N4. Subscribe for more tutorials from Math Zone African Motives.